We are a very lean startup with zero overhead, actually. And I think we were the first startup in the partial reprogramming space, as we started in early 2017. And initially we planned to do an ICO to raise funding, but then the regulatory authorities kind of cracked down on ICOs, so we had to pivot to this minimalist configuration. And we decided that we're going to raise some initial funding through crowdfunding, and we pledged that we're going to spend it all on experiments. So all our team members agreed that they will donate their time and expertise to the project for free. And here are these wonderful human beings. We have a 5-person team that is distributed across the world, from Moscow to St. Petersburg to Israel to Canada. And so we have zero overhead, we have no lab, we have no office, and we tend to keep it that way because we want to outsource the experiments to CROs or to have partnerships with established researchers who have a lab. So to keep our minimalist lean configuration for now. We have wonderful advisors whose expertise is very valuable to us, and I'm sure some of these faces look familiar, so I won't dwell on this slide too much, especially now that I learned I have half the time that I was initially promised. So here's our philosophy. Okay, thank you. We are very radical life extensionists, so compression of morbidity or health span increase just don't excite us. We actually would like to add decades, if not centuries, to the human lifespan, and obviously we want to help humanity reach longevity escape velocity. So we paraphrase 50 Cent, get to reach LEV or die trying. Hopefully we don't die trying. We are very mission-oriented, and here by mission, I mean our global mission to defeat aging. We think this is the #1 priority for humanity. So in our value system, added years of life are just much more valuable than the dollars you can make off of these projects. But don't get us wrong, we have nothing against making money, and we certainly recognize the high commercial potential that rejuvenation therapies will have. But we just don't view other companies as competitors. It's even in the same therapeutic paradigm, and now there are other companies like Turn Bio, like Live Bio, Reverse Bio. The bio seems to be like the magic word in the startup space, who are working on this paradigm. But we wish them every success, because no matter who develops this therapy first, we'll all enjoy the fruits of their labor. And for us, it's just much more important that the mission is achieved, that humanity manages to defeat aging. But so we think openness and transparency are very important to this joint mission, because in sharing knowledge, we can then help accelerate this day when 100,000 people won't have to die every day because of aging. But enough philosophy, let's get into the science of partial reprogramming and epigenetic rejuvenation. So here's what we mean when we talk about epigenetic rejuvenation. I'm sure most of you know that there are epigenetic mechanisms that ensure that our skin cell expresses different genes than our brain cell. But what people didn't realize, that there is some sort of epigenetic clock in our bodies that seems to dial down some genes and dial up others with aging. And to us, that kind of brought the question, can we reverse that aging clock and have systemic rejuvenation as an effect? And 2 crucial pieces of evidence that hinted that the answer to that question is at least a maybe are the groundbreaking Nobel Prize winning Yamanaka study in 2012 that showed that you can actually reverse a cell back into essentially embryonic state. And not only that, you can also rejuvenate it in the process, rejuvenate its molecular aging hallmarks. And then the next groundbreaking study was done in 2016 by Alejandro Ocampo, who's in this room, sitting right there, who showed that you can actually use Yamanaka factors in vivo, and you can kind of tame these reprogramming to safely roll back epigenetic age and prolong lifespan in at least the progetic mice by up to 50%. And there were early hints in nature and in the lab that this might be possible. First of all, there's social insects that kind of hint that aging is malleable, and even twins with the same DNA can have a 100-fold difference in their lifespan if one of them chooses the queen path, or doesn't choose really, but goes down the queen path and the other goes down the work path. The lifespan can differ by 100 times. And you can actually reprogram a worker termite to a queen termite, and that will bring all the added benefits of increased lifespan. Monarch butterflies, or for another example, those who live in the summer only live a couple of months, but those who live in the winter live up to 9 months, and same identical DNA. And also you can have a reversal, even reversal of life stages in some animals, like in beetles. When you starve them, they regress down a larval stage. And some jellyfish also are able to turn themselves essentially into an embryo and then regenerate again. And in science, we saw that you can also do the same, at least in the cells, with John Gurdon and Yamanaka later on, who showed that you can do this on a cellular level. And then on an organismal level, we saw this with parabiosis, which I'm sure many of you heard, but for those who don't, it's when you join the blood supply of two animals, for example, a young and an old mouse, and you see that the old mouse is somehow rejuvenated. And this, first of all, is important because it shows that aging is potentially reversible, and second, that there could be some signaling factors in the blood that can accomplish its reversal. Another discovery was the epigenetic clock, that we have this clock that goes up with aging and is not only synchronized across different people, but is also synchronized across different tissues. This is the most accurate Horvath clock that was seen to be showing the same time in very different cells, like in blood cells and brain cells, which are very distinct. You know, one of them stops dividing even before birth. Your neurons, they don't divide anymore. And blood cells, they never stop dividing. And yet, they show the same epigenetic clock, which is, hinting at some conserved epigenetic processes that happen with aging. And what is more even interesting is that you can use the human Horvath clock on chimpanzees, and that also pretty accurately predicts their age. So obviously, there's some evolutionary conserved epigenetic elements to aging. And also what we see is that when you do some known life-extending interventions, they also slow down or decrease epigenetic age, which again shows that there's some very interesting science going on the epigenetic control of aging. The monumental study, the giant on whose shoulders we'll stand upon, is Shinya Yamanaka and Takahashi, who in 2006 showed that you can reverse the cell back into essentially embryonic state, and as I said, on the way you can rejuvenate many, if not all, cellular hallmarks of aging. And this was shown in 2006, and after that it kind of opened the floodgates of research into this reprogramming process, and other researchers showed that you can actually restore mitochondrial function of a 100-year-old fibroblast down to 100-year-old donor of a fibroblast to essentially youthful levels. You can restore mitochondrial function by this epigenetic reprogramming process. And then another groundbreaking study, another giant on whose shoulders we stand upon, is Alejandro Campo and his colleagues from the Salk Institute out of the Belmonte group, who showed that you can use these Yamanaka factors in vivo, and you can ameliorate or slow down the hallmarks of aging, and you can increase lifespan in progeric mice, in this case, by up to 50%. And this landmark study really kind of set in motion a lot of other companies in our field, and this process is now, I think, getting more notice because of the work of Alejandro and his group. So enough of, wow, I'm going already into questions. That was the science that kind of inspired us on this process. And here is our therapeutic paradigm, which we're exploring. We think that we need to really slow down the exponential increase in the mortality rate that we observe. I mean, we're used to seeing this graph, the increase of our odds of dying in a logarithmic projection, but it's not very illustrative, because if you look at it in a linear projection, you see just how explosive this growth of mortality is. And we really want to do what other animals like turtles really know how to do, is to stop the increase in mortality rate. And our mortality rate is actually not that high. For a 60-year-old person, the chances of dying, annual chances of dying, are just 1 in 100, which means that if we can freeze that mortality rate, just purely mathematically, that person can extend his life or expect to live another 100 years. So we think that with periodic epigenetic rollbacks, we can accomplish this. We can fix this mortality rate at a certain level and have a 60-year-old be biologically fixed at this age and this mortality rate for decades. Of course, if we're not betting that we can miraculously turn a 60-year-old into a 30-year-old with one expression of Yamanaka factors. If that happens, great, but we really want to have at least a fixation of their increase in mortality rate. And how we plan to do this, obviously you don't want to have gene therapy delivered on a monthly basis if you're targeting monthly rollbacks. We would like to deliver the genes just once, the rollback genes, deliver them just once, and then activate them on a need-to-be basis, whether it could be monthly or biweekly or whatever, that will be established in later research. Why is this possible? Well, because luckily the reprogramming process happens gradually. So before a cell stops being functionally a skin cell, its epigenetic age is gradually reduced, and like the blue line on these graphs. So we can potentially decouple this process of epigenetic rejuvenation from the process of the cell losing its identity. And we can target this therapeutic window where this blue line, this epigenetic age, is already reduced, but the cell still remains a fibroblast. It still remains functionally the same cell that started the process of reprogramming. And how can we widen this window? One approach is to use just one of the Yamanaka factors, OCT4, and I'll really try to accelerate because we wouldn't have enough time for questions. We use crowdfunding to try one of the factors, OCT4, to have an experiment to use it in human fibroblasts. So we had the successful crowdfunding campaign. Why did we pick OCT4? Because it's the kind of initiating reprogramming factor, the guardian of epigenetic gates, as some people call it. And so we created this vector, this lentivirus, that transfects human fibroblasts and uses OCT4 in an inducible fashion, like using doxycycline, like it was used in mice. And so this experiment is still ongoing, but we hope that this OCT4 by itself can reduce epigenetic age without having cells lose their reprogramming, lose their identity. And our next R&D goals is to try to make this therapy even safer. First of all, we want to try to avoid teratomas by avoiding fast-dividing tissues, avoiding expression of Yamanaka factors in those tissues, and we want to try other approaches of inducing Yamanaka factors, even maybe using CRISPR to activate endogenous Yamanaka genes. And we have some other items there. We're happy that there are other researchers who are exploring this paradigm, which means we can partner with them and we can use their expertise and their lab space to have joint experiments if we're successful in raising funding. One potential collaborator is Dr. Rodolfo Goya in Argentina. He's already been doing a lot of this work of in vitro partial reprogramming, and we hope that we can continue work with him if we raise some funding. Alejandro Campo, who I mentioned, we have a very similar understanding of how epigenetic reprogramming works, and we have some potential ideas about in vivo experiments that we'd like to explore if we do succeed in raising funding. Transgenic pets is also on our to-do list, and David Ishii is a very known genetic biohacker and dog biohacker, and it'd be remiss not to collaborate with him. We have 2 minutes left for business. Very simple commercialization strategy, 2 tracks, one for pets, one for humans. GMO pets is one idea because the pet market is huge. It's almost $60 billion. So we think both transgenic pets, long-lived transgenic pets, and gene therapy for regular pets will be in demand. And for human market, cosmetics is the obvious application because it's already in itself is a $500 billion market, and regulatory barriers are somewhat lower there than for therapeutics. But obviously, the regular therapeutic pathway, systemic rejuvenation is our holy grail because true rejuvenation therapy will be preventing all the age-related diseases, and just Alzheimer's alone is, I'm sure, will be a $1 trillion product if you can prevent Alzheimer's. So here are our milestones. The transgenic pets with the Yamanaka factors are kind of our MVP, minimally viable products. And after that, we'd like to explore gene therapy for regular pets. And obviously, at some point, we want to enter clinical trials for humans. And so, yes, just one. No, almost done. That's right. Our fundraising, right now, as I said, we're very lean. We're early stage, so we're raising just $500,000 for the translational questions we need to answer whether this paradigm can actually be translated into a therapy. And we want to test some OCT4, as I said. And the next round would be $2 million to test the more expanded paradigm of implementing safety in our system to avoid, say, for example, overexpression of Yamanaka factors. And with that, I thank you. If you have any questions, please email me or we can talk afterwards. Thank you very much.